So ultimately, that's the goal here. Try to rearrange the original equation that's given so that you have all the y's on one side, all the x's on the other. Now normally, since these are presented where it's dy over dx equals something, cross multiplying is a good place to start. We cross multiply. On this problem, it's pretty convenient because you'll notice with this first diagonal here, we've got y times dy. And for the second diagonal, we've got x squared times dx. This problem's convenient because right away it gets all the y's on one side and all the x's on the other. And if our goal here is to essentially go backwards to what we remember about the implicit technique, well, with the implicit differentiation technique, we were taking derivatives. Here, we want to take antiderivatives. What I do is I apply an integral to both sides. If I try to integrate the left side, so take the antiderivative of this function y, following what I know about my antiderivative rules, this power is 1 on the y, so I'm going to add 1 to that power. I'm going to take that reciprocal, which would be 1/2, and stick it in the front. What that is going to equal, well, same rule applied over here to my one function of x squared. That's going to be 1/3 x cubed. Now these are not definite integrals that we're applying to each side, right? We don't have values here defined as an interval, so we got to tack on that plus c again. And ideally, you know, this is an okay answer. A lot of times, though, you'll see us clean up the fractions. You know, maybe try to clear these denominators out. A quick way to do that, common denominator between 2 and 3 would be 6, so maybe multiply everything by 6. If you multiply 6 by 1/2, you get 6 over 2, which is just 3y squared. If you multiply 6 by 1/3 over here, distributing all the way through, well, that's 6 over 3, or 2x cubed. And if we take this 6 times this constant value, yeah, we could say it's 6c, but usually what we do is we just change the variable we're using for the constant to say, hey, this is something different now. So maybe I put a d in there or a k in there instead, just to distinguish the variable. But that's it. All right, on this one, we'll let dy dx equal 1 plus x over xy. Like we discussed on the previous problem, you're trying to get all your x's and your y's together on one side. Normally a convenient way to do that is to cross multiply. So if I cross multiply here, look at this first diagonal, I've got xy multiplied to dy. And then multiplying on the second diagonal, I've got this dx multiplied to the 1 plus x. 1 plus x is basically a quantity. We're sticking the dx at the end. All right, this problem's not as convenient as the first one because we don't automatically get all the y's on one side, all the x's on the other. But this x that we currently have over here on the left-hand side, we could divide both sides by x. That would cancel my x from over here. And now I would have y dy equals be this quantity of 1 plus x over x dx. Once you have your y's on one side, your x's on the other, go ahead and throw your integration symbol in there. Take the antiderivative of each respective side. Got a similar situation as before on the left side. It's y to the first. So we know that's going to be y to the second, reciprocal 1/2 to the front. This other side, we're trying to take the antiderivative of a quotient, which we know doesn't really work too well. And a lot of times what we do is we just bring this x up, right? We're hoping we don't have to use substitution, but remember, substitution is a possibility on these. But we're hoping we can avoid that altogether. If we bring that x up, haven't taken the antiderivative yet, so I'm leaving my integration symbol in there. Bringing the x up, you've got x to the negative first, times that quantity of 1 plus x. dx. Now you've got a product, still can't take the antiderivative of a product. Sometimes you got to use substitution again, but here we could distribute, which would be nice. That means we could avoid all that substitution. And when you distribute, still haven't taken the antiderivative, you've got x to the negative first plus, now let's see, it's x to the negative first times x to the first, right? If you add your exponents, you've got x to the 0. So that's just going to be 1. So there's what I need to take the antiderivative of. I'm going to go ahead and carry this over to the next page since we're running out of room. Let's see, what am I carrying over? X to the negative first plus 1 dx. All right, so if this is where we've left off, going through taking the antiderivative now of this right side, left side's already taken care of. Well, let's see here. X to the negative first. It's been a little while since we've had to take the antiderivative of something like that, but this is supposed to stand out to us as a special antiderivative. You remember what that answer is? X to the negative first is the same thing as 1 over x. The derivative of what gives you 1 over x? You remember? That ring a bell? If you took the derivative of the natural log of x, you get 1 over x. So this was the special one. If you got a power of negative 1, antiderivative is natural log of the absolute value of x. For this plus 1, if you just have a constant, what's the rule with antiderivatives? You just attach an x, and then we've got a plus c that we've got to tack on. Okay, so how are we doing to this point? Good? Kind of like we did on the previous problem. You know, if you got a fraction in there, we can clear that out. Ideally, this step we're at, it's an acceptable answer. But if I clear this 2 out, multiply everything by 2, I'd have y squared equals 2 natural log of the absolute value of x plus 2x. Once again, instead of saying 2c, just kind of change your variable here to represent a different constant value. We could say plus d, plus k. Just choose something else.